So today I want to go over a few more examples of working out proofs for identities of trig functions. And I want to start by looking at the one that I asked you guys to think about at the end of the previous video, where I said you guys should take a minute and see if you can figure out how to prove this identity. It's really very similar to the way that we did the last identity in that video, in fact. We proved a similar identity that involved, instead of cosecants and cotangents, we had secants and tangents. Now, I'm going to show you how to do this just using one method. There are actually several different approaches that are all kind of natural and will work very well. But the way that I'm going to work this one out is I'm going to rewrite this left-hand side as cosecant squared theta times cosecant squared theta minus 1. Okay, well now I need to use an identity here. In fact, I need to use a couple of identities. So, well, really one identity, but I need to use it twice. And so what I want to remember is that the Pythagorean identity applied to cosecants and cotangents says that 1 plus cotangent squared theta is equal to cosecant squared theta. So remember, there's the three different forms of the Pythagorean identity, and these three different forms, one of them relates to cotangents and cosecants. So now what I can do is I can replace this cosecant squared with 1 plus cotangent squared, or cotangent squared theta plus 1. I'm going to write it this way instead of the other way. It doesn't really matter, but this way everything is going to come out in the same order. Now, from this identity, which we've established because it's really just the Pythagorean identity, so we don't need to worry about proving it or anything, I can also see that cosecant squared theta minus 1 is equal to cotangent squared theta. So everything inside this parenthesis set, this expression is going to come out to be cotangent squared theta. So we've taken the left-hand side and we've written it entirely in terms of cotangents. And this is good because, well, the right-hand side here is all in terms of cotangents. So now I'm just going to multiply everything through here, and we get cotangent to the fourth theta plus cotangent squared theta, which is actually exactly the right-hand side of the original expression. And so we are done demonstrating that this identity is true. If you go back and you compare this to the one that we did with secants and tangents, you'll see it's almost identical. In fact, the only difference is that we replaced all the cosecants with secants and we replaced all the cotangents with tangents. Now, just like that previous example, another approach to doing this would have been to rewrite everything in terms of cosines and sines, and that would have worked fine. It would have been a little bit longer than what we did here, but it would have gotten you to the same place in the end. The advantage to doing it that way is that you don't have to worry about these forms of the Pythagorean identity. You just have to remember the standard one for sine and cosine. Now, because these are all a little bit different, because they can be a little bit tricky, I thought maybe I would go over just a couple more examples of working out these identities for you today before we go on to start talking about more identities that hold for the trigonometric functions. So I'm just going to grab some examples here. Yes, here's the one that I wanted to do next. 3 sine squared theta plus 4 cosine squared theta is equal to 3 plus cosine squared theta. Now, when I see a problem like this, I usually try to start by simplifying the side that's more complicated. And this left-hand side looks more complicated to me. So I'm going to begin with that side. Now, when I look at this, I sort of think about this and I say, well, this looks a little like what we get in the Pythagorean identity, right? Sine squared plus cosine squared. Except it's not just sine squared and cosine squared, it's got these coefficients out front. But let me rewrite this left-hand side in the following way. I have the 3 sine squared theta, but I have a total of 4 cosine squared theta. I'm going to rewrite that 4 cosine squared theta as 3 cosine squared theta plus cosine squared theta. There are 2 reasons I want to do this. There's 2 reasons I would think to do this. One reason is because I have a 3 out front of the sine squared theta, so I would like to have a 3 with the cosine squared theta as well. The other reason is because I notice that on the right-hand side, I have a cosine squared by itself, and if I split this into 3 cosine squared plus cosine squared, well, now I also have a cosine squared by itself. Okay, so I'm trying to explain here kind of my thought process, but your thought process might be a little bit different, and that's fine. Now what I can do is I can factor the 3 out of these first 2 terms. So I get 3 times sine squared theta plus cosine squared theta. And then outside of all of that, we're still adding on the cosine squared theta here, of course. But this is just 1 by the Pythagorean identity. So this becomes 3 times 1 plus cosine squared theta. But of course, that's just 3 plus cosine squared theta, which is the right-hand side to begin with. So we are done. We have proved this identity. I want to reiterate that when you are proving these identities, you don't want to just assume they are true and start messing with both sides at once, okay? It's tempting to sort of say, oh, we have an equation. We can start doing things to both sides. Well, the problem is that subtle issues can crop up when you start doing that. And it's usually not worth trying to do it while avoiding those subtle issues. Basically, the issue that you can come up with when you do that is you might end up multiplying or dividing by 0 by accident. And you don't want to multiply or divide by 0, of course. And for that reason, it's just simpler to say we're just going to simplify one side at a time and see if we can get both sides simplified to the same thing. Often, you can just simplify one side and you end up with the other side. All right, so hopefully that made sense to you guys. Let's take a look at another problem here. So let's take a look at give me a second while I pick out a problem here. Okay, so I was just taking a minute to look through these problems, figure out a good one to do. I think this one is going to demonstrate some methods that we really haven't seen before. So, when I take a look at this problem, there are a couple of different approaches that I could take to doing this. So I'm going to show you kind of the long way, and then I'm going to show you the shorter way that I noticed to do it. So the long way, I would say that this left-hand side is more complicated because cosecant is defined in terms of other things, in terms of sine in particular. So let's attack the left-hand side and see what we can do to simplify it. Now, if I rewrote this left-hand side in terms of sines and cosines, I could say, well, this is really 1 over the sine of v minus 1 divided by 1 over the sine of v plus 1. If I wanted to now, I could start taking a common denominator here and combining these fractions. So if I were to do that, I would need to multiply this by sine v over sine v, and this by sine v over sine v. So this would become 1 minus sine v all divided by sine v. And then that whole fraction is going to be divided by 1 plus sine v divided by sine v. But dividing one fraction by another fraction, remember, that's just the same thing as multiplying by the reciprocal. So this becomes 1 minus sine v divided by the sine of v times sine v divided by 1 plus the sine of v. This is a really silly looking v. Let's make that a little easier to read there. And now we notice that the sine v's cancel and leaves me with 1 minus sine v divided by 1 plus sine v. But that's the right-hand side, so I'm done. Okay, so that worked perfectly well. That's great. I want to show you now, well, first of all, take a moment, pause this, make sure that you fully follow everything that we just said. But now I want to show you a slightly quicker way of doing it. It's really the same idea as what we did here, okay? In a lot of ways, it comes from an observation that I made when I was glancing at this problem. And I noticed that I could do this much faster. So, the way that I noticed that I could do this faster, instead of simplifying the numerator and the denominator of this compound fraction separately, I noticed, well, what would happen if I just multiplied this entire thing by sine of v divided by sine of v? Because if I did that, these would cancel and leave me with just ones, and these would turn into minus sine v and plus sine v. But that's exactly what I happen to have on the right-hand side. In other words, instead of just simplifying these expressions separately and then trying to see what cancels, I'm just asking what would happen if I just multiplied this whole thing through by sine v on the numerator and the denominator. Well, the answer is that this immediately turns into 1 minus sine v over 1 plus sine v. And so we are immediately done. Now, I want to recommend to you guys that if you want to make sure that you've understood this, take a look at problem 49 on page 641 of your textbook. This is in chapter 6. This is in chapter 8.4, and this is a similar problem that requires you to do some pretty similar kinds of things here in order to solve it. All right, let me pause this again for a second, pick out another problem. All right, so I picked out another problem which I think is going to kind of show us just a little bit of a different thing. Like, I want to try to give you guys examples here that require different sort of thought processes to solve them. Now, when I was looking at this problem, at first this problem looks like quite a mess. It looks like it's pretty horrible to try to deal with. But then I started looking at this and I thought about, okay, the left-hand side looks more complicated, but the right-hand side does have this tangent and tangent squared business going on. Let's think about what that would really be. So the right-hand side, this would really be sine theta divided by cosine theta, all divided by 1 minus sine squared theta over cosine squared theta. Okay, that doesn't necessarily seem initially like it helps us a great deal. There are a couple of things that we could do at this point. We could try to simplify this whole mess. In fact, maybe that is what we should do first, and then I will show you the sort of shorter method that I came up with for doing this. So if I were to just start simplifying this right-hand side, I would get sine theta over cosine theta on the top. On the bottom, if I take a common denominator here, I would end up with cosine squared theta minus sine squared theta, all divided by cosine squared theta. Just like in the previous example, we can now say that dividing by this fraction is the same as multiplying by the reciprocal. So this is equal to sine theta over cosine theta times cosine squared theta divided by cos squared theta minus sine squared theta. And one of these cosines cancels with one of these cosines, and we end up with sine theta cosine theta divided by, okay, I can't write apparently, cosine squared theta minus sine squared theta. So we started with the right-hand side, and we eventually simplified things down to the left-hand side. So we are done. Now, once again, this is not actually the first way that I saw to do this. The first way that I saw to do this was a little bit different, but make sure that you understand what happened here before we look at this second method. So the way that I actually thought about doing this initially was I thought about the fact that tangent is sine theta over cosine theta. And I thought about how would I go about starting with this left-hand side and getting a tangent theta there. Well, the answer is to go from sine theta cosine theta to sine theta over cosine theta. I would need to divide the numerator by cosine squared. So what would happen if I did that? If I took sine theta cosine theta, and then of course we have in the denominator cos squared theta minus sine squared theta, if I wanted to turn this numerator into a tangent, I could do that by multiplying this by 1 over cosine squared theta. But I can't only multiply the numerator. I have to do the same thing to the denominator. So, let's see what happens when we do that. And the neat thing here is that it's just going to work, which is good. I mean, maybe that's not always going to happen, but you can you try it and you see. You know, there's no harm in trying it. If it doesn't work, then we go back and we try something else. Okay, so what's going to happen here? Well, this cosine theta is going to cancel with the squared. And that's going to leave us with sine theta over cosine theta in the numerator. What about in the denominator? Well, the cosine squared, when I distribute this fraction into this expression here, the cosine squareds cancel and leave me with 1. And then I have minus sine squared theta over cosine squared theta. Now, at this point, this should look familiar from what we were doing a minute ago with our first approach to this problem, because actually we got to this step when we were messing around with the right-hand side. That's because sine theta over cosine theta, that is just tangent theta. And on the bottom here, what do I have? Well, I have 1, and then I have sine squared over cosine squared, which is tangent squared. So 1 minus tan squared theta, which is the right-hand side, and so I'm done. Okay, so you can kind of see here, there's two kind of different ways of doing it. They are related. I mean, they're very closely related. This is not super surprising because we are still trying to establish the same fact, but they do involve slightly different thought processes maybe. And so for some of you, one approach might seem more natural than the other, and that's fine. Do whatever comes naturally to you. Now, at first, none of them might seem like they come all that naturally. So at first, you might find yourself saying, well, I'm, just going to have to try stuff and see what works. And that's okay. Sometimes you try something, it doesn't work. That's fine. You just realize, okay, that doesn't work. And sometimes seeing why it doesn't work can help you go back and figure out what does work. Okay, so if you are trying to prove one of these things and it seems like it's going nowhere, don't just give up and start over from the beginning. I mean, you do maybe want to start over, but ask yourself, okay, why wasn't that working? If what would make it work instead? And you really do kind of have to get used to thinking through these like a little bit of a puzzle. Now, if you want to try a similar problem to this one, actually, I don't really see any very similar problems to this one, but problem 63 looks like it's a little bit similar to this one if you want to give that one a try. It is somewhat different, but I do recommend that you try it out. All right, so I think hopefully you guys have seen some examples from this that can help you as you work through the problems. Now, I also want to emphasize you guys need to be watching the My Math Lab videos on this as well, because they give you more explanations for how to think about this stuff and more kind of examples and ways of thinking about this that maybe will help you guys to figure out the problems on your own. But these really are the sorts of things you have to practice on your own. So I'm going to leave things off there for now, and next time we'll be talking about some additional identities that hold for the trig functions.